Good morning, everyone. Thank you for joining today's PCI SIG webinar, Scaling AI and Cloud Infrastructure with PCIe SIOV. We'll get started here in just a moment. Good morning, everyone. Welcome once again to today's PCI SIG webinar, Scaling AI and Cloud Infrastructure with PCIe SIOV. Go ahead and take a moment to introduce today's panel. Our moderator today is Scott Knowlton. He is Senior Director, Product and Solutions Marketing Manager at Synopsys. So I have Stephen Bates, Fellow AI Storage Software and Architecture at AMD. Utkarsh Kakaya, Technical Director of ARM. Jake Oceans is Distinguished Engineer at Microsoft. And Rob Sykes, Director, ASIC Technical Product Management at Micron. So I'll go ahead and pass it over to Utkarsh, who will present today's introduction to SIOV.
Thanks, Kevin. So let's walk through what are the key motivations for building SIOV, right? So if you look at today, for data centers, many times services run with virtual machines, right? And what we have seen over the years is that there are lot number of cores per server. Sometimes the cloud service providers build machines with a 2-socket, 4-socket, 8 sockets. So we're seeing a growing number of cores and growing number of virtual machines. So there's also been a lot of new deployment around containers, where earlier the services which used to run in VMs are now running in a container. And when you go to container, it's a lot more scaling compared to virtual machines. So for this virtual machines or containers, when you want to do accelerated networking or do accelerated storage, or you want to do AI ML workloads from these containers or virtual machines, typically today we use a PCI pass-through, where you assign a PCI device to a virtual machine or container. Your device is capable of SRIOV. Sometimes you assign a virtual function to this container or a virtual machine. However, as we go into more scaling, we need a more scalable approach to assign devices. That is where we were looking into scalable virtualization, the technology to scale from hundreds of assignable interfaces to thousands of assignable interfaces in future. The other thing which is also driving or changing in the environment is that earlier people used to run virtual machine in a virtual environment. Now they're running nested virtualization, where imagine you have a cloud server where you have multiple big VMs. Within those big VMs, there are small VMs or containers running in the cloud. So you need a way to subdivide the interface you are assigning for this particular virtual machine or container. And today, with SRIOV or PCI pass-through, that subdivision is not possible. So we need a better way to subdivide sources. Also, with the use of cloud and AI, a lot of time where you have a lot of new requests or search queries coming into the server. So you need to dynamically increase the capacity of a VM or container based upon the demand, and then later on reduce the consumption. So we need a way to, so a good example could be a web server running in a cloud where I'm running right now 100 requests. Suddenly I see a need to handle 1,000 requests. So I need a way to dynamically assign more resources to that VM or container. Later on, when it's not being used, reduce the resources for that particular container. Now let's look through how this is being solved today, right? So we talked about the PCI pass-through or SRIOV. With those approaches, the challenge is that when you want to build a PCI function or a virtual function, each of those functions needs a dedicated configuration space, a dedicated bars, a dedicated interrupt tables for MSI or MSIX. And with thousands of interfaces per device, the amount of cost you spend in building the extra hardware, welding the extra hardware, and also consuming address space in the platform, it's not really scalable. Other thing also we're noticing is that in the cloud, a particular server may be running a mixed workloads where you have small VMs and larger VMs, where each VMs may have a different needs. So for those scenarios, also we need a way to actually assign resources based upon demand or based upon the need, And with the SRIOV virtual function, the requirement is that each of the VFs are of similar size, which ends up adding extra cost on the hardware to actually create some additional mapping between what is the exposed MMI of bar versus what is actually implemented in the hardware in terms of work use. And finally, we're also seeing with a more deployment of IPUs and DPUs in the cloud, a need to create a compose interface where you have one interface which is like a NIC, other interface could be a NVMe. So we need a way to have more flexibility on device types you expose from a same physical device. So those are the main drivers for change, right? We need a way to scale better going forward. We need a way to compose the device interface based upon the need of a container or VM. We want ability to kind of subdivide it for initial virtualization. And finally, we also need a way to have different device types exposed from a same interface. So that's the main motivation driving the SIOV. Now let's look through what is SIOV, right? So SIOV is a newly developed hardware-assisted I/O isolation technique, which we have currently included as a part of PCIe Base Specification. So if you download a PCIe 7.0 spec or a 6.4 spec, you would see SIOV described in that specification. As a part of SIOV, we describe a new lightweight interface called Scalable Device Interface, or as SDI. It's more of a lightweight and composable, where you don't need to build a config space for the SDI separately. You don't have a separate bars for SDI. You don't need to have a separate MSIX table for SDI. So it helps you to kind of scale the hardware by making it more lighter weight and composable. And finally, we also leverage the fact that control path operations are not frequent, whereas the data path operations like the doorbell writes and interrupts are more frequent. So we kind of move some of those control path operations to the software and virtualization environment, and then keep the data path still going directly to hardware from the VM, thereby keeping the performance. So to go in additional detail for SDI, as I mentioned, doesn't have a config space. If the software wants to expose the PCI interface to a VM, it can potentially create config space in the software to emulation. There's no dedicated bars for SDI, so SDI share a bar of a physical function where SDI is hosted. There's no separate tables for the SDI, so you can potentially share the physical functions table among SDI, or you can have a device-specific way of storing the SDI interrupts. So here is where we provide a way for the driver to decide where it wants to store interrupts for SDI instead of defining in the spec. Finally, we also provide ability for you to have a different SDI types for same physical function. So I can have one PF with one SDI being a GPU, another SDI being a VPU, or one SDI being a NIC, right? So there's a flexibility on how you report the SDI type from the hardware perspective. And finally, we want to leverage the current interconnect abilities and also TA functionality. So we continue to use routing IDs for identifying the traffic from the SDI, whether it's a DMA traffic or interrupt traffic. So we leverage that for Scalable IOV. Now let's look at an example of a device and see how the SRIV differs. So on the left side, we have a picture where there's SRIV device, which has set of compute engines, IO engines, and there are a set of virtual functions exposed by this device. So I have a VF0 to VFN. Each of those VFs has a config space in the hardware. There is some MSIX tables for the VFs. There are bars for the VF. And there's some arbiter which is allowing you to share the physical hardware like engines or DMA engines within the device. On the right is an SIOV device where we don't implement those for SDI, right? So it is an example where there was a VM which needed two resources. So there's a SDI 0 composed with just two doorbells or queues, right? And there's another SDI with just one queue. So there's a way you can customize based upon the VM needs, how many queues or doorbells you want to expose for a particular SDI. And also for those queues, you can define a way to store interrupts as well. In terms of these queues, the way they're exposed is through the PF bar. So PF bar, you can create regions where some regions represents SDI 0, some represents SDI 1, SDI 2, and so on. Now, jumping to the software architecture, right? So we wanted to leverage the current software architecture and kind of extend it for Scalable IOV. So if you look at today, for most the hypervisors or VMMs, they already trap the config space for the PCI pass-through devices. Many times they also intercept the bars for example, for interrupt programming where they want to live migrate a VM. Sometimes hypervisors intercept the bar programming. Sometimes they also intercept MMIO regions for bar for security checks. So we wanted to leverage that. So the idea we came up with here was to actually expose a virtual device to a VM. The virtual device is composed of intercepted resources and direct map resources. So intercept resources means things which are intercepted by the host, example being the config space of a PCI device or intercepted bar regions. So for those intercept resources, the idea is to use the page tables in the MMU to actually trap that access from a VM and give the control to the host software. So that's why we have this VDCM composition module on the left, which is going to emulate that resources in the software rather than having hardware provide that. Whereas we want to keep the data path performant for the hardware. So the examples of queues are directly mapped to the SDI on the hardware. Similarly, the interrupts are directly mapped to go directly to VM. So this allows us to kind of keep the control path in software while keep data path directly in the hardware. And each device may have their own specifics on what does VDEV composed of, what are the interrupt sources, what are the data sources, and that's why there's a more bigger role given to the PF driver to decide how to provision the VDEV, right? So PF driver can say, for this particular device, I'm going to keep this resources in the software and this resources in the hardware. So there's what the SDI is means from a device perspective. It's nothing but a set of AMI regions, set of interrupts, and set of each area is SDI as a read, which is used for DMA transactions. So that kind of completes the high-level overview of SIOV. I'll hand over to Scott now, so we can go through some Q&As.
And so the way I'd like to do this is kind of start kind of at a higher level at the top and give you some motivations of why SIOV is being or was implemented into PCIe, and then we'll go into some more details. Sorry, am I still muted?
We can hear you now, Scott.
Okay, thank you. Okay, this panel's a little slow. So we're going to start with some high-level questions. So, Steve, where do you see the strongest demand for PCIe SIOV technology today, and which market segments will benefit most as adoption grows?
I think that's a great question, and it's good to start at a high level. And thanks, Utkarsh, for such a great kind of overview of what SIOV is from a technology perspective. So I think there's a couple of places that we're going to see SIOV adoption. I'm going to focus on one that's in the AI accelerator space. I think people like Jake can jump in on some of the other use cases that we see. But one of the use cases that I've been exploring for SIOV is in AI kind of supercomputing clusters where we tend to have a lot of devices that are not CPUs that are trying to get work done and trying to move data around. So, think of a large either training or inference cluster for a large language model as a service kind of deployment. In these kind of deployments, we might have, tens of thousands of accelerators, typically GPUs, but obviously there's also other types of accelerators that are good at doing matrix multiplies, which is the main thing that we use for AI. But they also need to move a lot of data around. We have to do forward and back propagations. We have to do batching. So as well as doing a lot of mathematics, there's a lot of data movement. One of the trends that we're seeing in the AI group at AMD is customers wanting to get accelerators to initiate some of this data movement. So we have a move from initiating, for example, an RDMA data movement across a network from the CPU to the accelerator. And we call this accelerator initiated IO. There's some other terms in the industry for this kind of thing. One of them is IBGDA, which is RDMA specific. But as a more general term, we have this accelerator initiated IO, where the accelerator would like to place elements on a work queue, ring a doorbell on an adjacent device, typically a PCIe device that might be a NIC or a storage device like an NVMe drive, and be able to do that. That's all very doable today, but one of the challenges is around security and isolation. And that's where SIOV becomes interesting, because SRIOV has challenges in the market because it's quite complicated. And I think in the kind of overview slides, you saw how SDI and SIOV can scale a lot better. So what we're looking at is a potential use case where SIOV can act as essentially a security isolation mechanism for device-initiated I/O and help prevent devices from either maliciously or accidentally initiating DMAs to places they shouldn't be initiating DMAs to. And we talked about the routing ID and how that can be SDI specific. So for example, it's now going to be possible to give a number of queues to one accelerator and a number of other queues from the same device to another accelerator, and have both of them have their own IOMMU mappings and IOVA tables, because they'll have different routing IDs. So I see this as a potential, like a really exciting potential use case for SIOV, and it's certainly one of the reasons why I'm kind of very much tracking and talking to other people in the industry about it. So I'm going to stop there because I think maybe someone else would like to jump in on that question and see what they have to say.
I would like to add to that. So one of my major concerns working on Microsoft's cloud is that we would like serverless computing to move more and more toward isolated containers. And we have a technology for that we call Hyper-V containers, which uses a lightweight VM around the container for stronger multi-tenant security. And every large cloud vendor has that. Google calls theirs gvisor, AWS calls theirs Firecracker, Kata containers is an example. There's a whole bunch. And I'm sure they're all different from each other, but their common theme is they wrap the container in a second level page table and make it a micro virtual machine. And if you want to carry accelerators of any kind or IO paths in their most lightweight fashion of any kind into those isolated containers, you need to use a strategy either like SRIOV or Scalable IOV. But when we go and we try and build devices, SRIOV tends to run out of gas around 1,000 virtual functions. People have trouble meeting timing going beyond 1,000 virtual functions, plus or minus half 1,000. But what we're trying to do with Scalable IOV is relax a bunch of the rules on SRIOV, recognizing that software has already evolved to the point where many of those rules aren't strictly necessary anymore. So by relaxing those rules, we make it cheaper in hardware to produce these interfaces, and we get into the tens of thousands potentially. And that matches the container scale we're looking for.
Anybody else? Okay. Karsh, so what real-world scenarios show PCIe SIOV technology's composability benefits?
So let's take a few examples, right? So one example could be that you have a GPU with a 1 terabyte memory, and if you expose that GPU with SRIOV, suppose you have 7 virtual functions, you end up spending 8 terabytes of region because you want to expose the same 1 terabyte either as a physical function or distribute 1 terabyte among the VFs. And what ends up happening is that because VF has their own bars, you end up consuming 8 terabytes of address space with just one GPU. And that is becoming a problem as today, where you have a lot more GPU with a bigger memory. Sometimes you also use physical address bits, upper physical address, this for some ID of a memory encryption keys. So by leveraging SIOV, we can avoid the address space expansion here by reusing the PF bar. So if you have 1 terabyte GPU, you just expose the 1 terabyte of the memory or MMIO space, and then let the software distribute that among the SDIs through the page tables. So that would be a good example for a GPU. Another example could be for a NVMe, where I have a set of queue pairs in the device, and I have a set of interrupt descriptors in the resources of the device. And now I want to give that to the secondary controllers where I want to assign them, right? So this is where the SDI composability helps, because you can say, I want to assign 2 queues and 2 interrupts to the first SDI. I want to assign the 5 interrupts and 5 queues to second NVMe controller, right? So with SRIOV, what ends up happening is that you ended up always over provisioning your addresses, whether it's MSIX table or the bar, and later on only mapping the required regions, which is a waste of both interrupt area as well as the MMIO space. And another good example would be the fat VM and mini VM example I gave right earlier in the intro, where clouds are running a mixed type of VMs, and you want to make sure that you don't waste the hardware resources to support different VM types from the same device. So that's why we are seeing that SIOV could be leveraged to help compose the SDIs based upon the requirement of a VM or container or a use case, to really not waste resources on the hardware or not waste address space for the interrupts or the MMIO.
Thanks, Karsh. So, sorry, did somebody else want to jump in there? Nope. Okay. So, Rob, how will PCIe 7 technology help to speed up the adoption of SIOV solutions?
Yeah, great question. So I think if I start with the motivation for PCIe Gen 7, I think that's pretty clear from what everybody was saying. AI, ML type of workloads really need PCIe Gen 7 performance over its previous generations. For SIOV, as you heard from both from Jake and Steve, GPUs, as they start increasing, or number of GPUs start increasing, the requirements on the workloads and the SDIs attached to those GPUs increases. So whereas SRIOV, I suppose, typically is in the tens to hundreds, albeit the specification allows up to 64,000. If you start scaling with SIOV to tens of thousands of SDIs, each one having a performance resource requirement, I think PCIe Gen 7 lends itself very well. At least gives you the overhead for managing all those that huge number of SDIs. But it's not just about performance as well. There's also a perceived lower system cost, or cost per bit. So PCIe Gen 7 improves efficiency over previous PCIe generations. So that makes SIOV enabled devices more attractive for high density deployments. And then there's the market aspect of it. So there's the future proofing. So as you heard, SIOV came in 6.4 and is now in 7.0. So as new devices start rolling out, SIOV is going to be there from the start. And then from a silicon vendor point of view, so anybody updating to PCIe Gen 7 will then, of course, have SIOV as standard in there. So, of course, it depends on Gen 6 which version you went with, but PCIe Gen 7 will be there from the off.
Okay, so carrying on to that, we're establishing, the technology, but then, Steve, why is the collaboration across the ecosystem important, right? CPU vendors, device vendors, OS providers, PCI SIG. Why is this important for SIOV adoption?
Yeah, I mean, that's a great question. This is a really important topic, because PCIe ultimately is kind of a point, it's a communication protocol that typically has, something as a root complex and something as an endpoint and maybe things in between. And it plays in a really tricky space in computer architecture where we kind of leave the, secure, coherent world of the, the main processor SoC and head out into, the external world where there's all kinds of challenges and interoperability issues and security issues. And, a couple of questions later in this panel dig into that a little bit. So I think for that reason, it is very, very important that, the main CPU vendors and the main device implementers get together in a forum like PCI SIG and in other forums like OCP and SNIA and talk about what it is that we're trying to do here and how do we do it in a way that is robust and secure. And I think security is one of those topics where if people aren't talking to each other as these kind of standards develop, there's going to be problems later down the road. There's going to be holes, there's going to be gaps. And as soon as there's any gap in a security kind of world, we have big, big problems. So I think it's incredibly important that these people talk. PCIe devices tend to have to talk to things like IOMMUs, and we have a whole bunch of PCI SIG features that allow us to do things like that. And SIOV is something that builds on top of all of that to give us, a really rich suite of capabilities as we try to scale the number of virtual devices that we would like to be able to have in a system compared to the number of actual physical devices that there are. I'll let other people jump in on that, but that's my thoughts there.
So kind of expanding on that and kind of going, so that we're talking about ecosystem, but then, looking internal to the devices, Steve, how does the SIOV technology adoption change the way system architects thinks about balancing hardware complexity and software complexity?
So a couple of weeks ago, Jake and I had a great chat. It was on a Friday, I remember, because my brain was fried afterwards. But one of the things we talked about was exactly that. How do we find the right balance between what a PCIe device implementer has to do and what can be done, either in software or some kind of offload engine on the main processor complex. And I think one of the things we see with SRIOV is that we fell too much on the side of putting the onus on the device vendors to implement a whole bunch of complexity that was quite rigid because you're implementing it in a PCIe endpoint. So, you don't have a lot of flexibility there. And B, just ended up resulting in something that was very hard for endpoint companies to implement. We don't see a lot of SRIOV out there, especially, in some of the lower end devices. But SIOV, I think, takes a better approach because the reality, and, I'm going to steal a phrase from Jake here, but the reality is, hypervisors today, even with SRIOV, will do some kind of intercepting on the control path today. I mean, we black out certain parts of the config space. We don't allow virtual machines to look at certain config register spaces, or we even present the virtual machine with a non-real version of those config space entries because we don't want an untrusted VM to know what brand of NVMe SSD is in that particular system, for example. We do an awful lot of virtualization around what is the kind of networking that we have, what is the kind of NVMe we have. So even without SIOV today, hypervisors are already doing a whole bunch of different things. I've always felt like the inability to have different device types with SRIOV was a really bad limitation. We want to be able to present storage devices, networking devices, accelerator devices, all from one physical piece of hardware. And that's what SDIs enable us to do. So I can now, take a PCIe endpoint that's SIOV capable, and I can take its resources and carve some of them out to make them look like storage, some like networking. I think that's a much better solution, and we're going to see a lot of software development work around that in open source frameworks like the Linux kernel's KVM subsystem, QEMU, and then Hyper-V and some of the other proprietary OSs will be doing their own implementations as well. So I think that's
let me take that as a springboard to try and answer a couple of the questions that have come up from attendees here. There have been a couple of questions here about what we actually need to do in software, whether standardization happening in the Linux kernel. Let me start by observing that the history of the last 15 years or so of SRIOV has led to every hypervisor having extensions that are, as Stephen said, not strictly implied by the SRIOV specification. And in Linux, that takes the form of VFIO integrating with the PF driver and perhaps with other components. What we really expect happens here is those things which may be considered quirks in the Linux kernel today become more the way things are done in these devices rather than the way errors or other things are patched over. And for the most part, that support already exists. The ability to intercept parts of configuration space, the ability to intercept parts of virtual bar space. And so one of the other questions that's in the channel there is, do we expect these devices to look like full PCI functions? And the answer is, for the most part, yes. That will be the common use case. There are discussions of being able to, for instance, if you wanted to map an accelerator into every user mode process on a machine with 1 million user mode processes, you wouldn't want to model that as a PCI function. You wouldn't want to pretend that you have a PCI function for every one of those 1 million user mode processes. And so it is also possible that other software models will emerge and that we will not be trying to make these look like PCI functions. But for the virtual machine and container use case, that seems like where we will certainly start.
Anybody else want to jump in here? Okay, so kind of carrying on from, there's been some conversation about, I'm going to jump around here a little bit, because of some of the questions here around there's some conversations about what's the difference between SRIOV and SIOV. And so that leads to a very obvious question here, which is, are there interoperability challenges between when mixing PCIe SRIOV and PCIe IOV, SIOV devices in the same system? So Rob, you want to take a shot at that?
Yeah, sure. So yeah, I mean, there are challenges in doing that, but it is being resolved. So if I list some of the challenges, so different capability structures, enumeration and resource allocation, and there's different drivers and hypervisor support, different interrupt and DMA handling, security and isolation is all different. So on the face of it, you would seem to think that perhaps they shouldn't coexist in the system, but as SIOV is very much software driven, there's no reason why operating systems can't adopt the SIOV side of it at the same time as supporting then more hardware-based SRIV as well. So, OS and hypervisors are implementing SIOV now, from my understanding. So they're being updated to recognize SIOV SDIs. so they will coexist for some time, and that will allow then a nice migration for people who start to think about SIOV and wanting to move from SRIOV to SIOV over time. So there's no reason why they don't coexist right now, despite all the different hardware aspects of it.
And so let me add to that. The way we defined SIOV carefully in the PCI Express space, it does not require the root complex to change its behavior in any way. So we do not need new processors. We do not need new root ports. We do not need new switches. We do not need any of these things, because all of the routing is done by requester ID and routing ID. What we do need at a system level is the firmware to understand a new capability structure and do the same bus number allocation kind of dance that it does with SRIOV with Scalable IOV. It is a different capability structure. It's actually pretty similar. So the burden of change on something like UEFI is actually very small, but it exists. Most of the change is in device design and in the software, the device drivers associated with it, particularly the PF driver.
So Jake, continuing on, so from a cloud operator's perspective, what operational benefits do you see in SIOV technology bring compared to traditional IOV models?
So I am a cloud operator, and I design these systems for Microsoft's cloud. So when I talk to a chip designer internally or a chip vendor wanting to sell to us, what I say to them is, I don't care whether you use SRIOV or Scalable IOV. What I care about is whether you can hit the scale we need for our container systems. So if you can build your device with 20,000 virtual functions in SRIOV, that's fine with me. But most designs can't do that. So the operational benefit is I can carry an accelerator or an I/O interface all the way into the customer's container, rather than running a paravirtual software layer in the container hosting VM or in the host or somewhere else in the system. And those for high-speed I/O and for certain accelerator scenarios, we could be reserving, depending on the workload, between 10 and 30% of the cores just to run those paravirtual layers. So the operational benefit is either the costs of the cloud vendor are lower, and thus that translates into the cost for the customer, or just more cores available to the customer to do their own work rather than the paravirtual layer penalty.
So then why is it easier and more natural for existing virtualization software stacks to migrate to SIOV?
It's not. I don't believe that. I think that it's a lot of software work to do this. I think that the natural thing to do is to continue on with SRIOV, and the only motivation to move away from it is to hit the scale for container systems, or for mapping things directly into user mode processes when you have a whole lot of processes.
That makes sense. So Ukarsh, so what's the overall impact of SIOV technology on the device driver software compared to SRIOV?
So if you look at the intro slide, we covered the virtual device, right? Your virtual device had intercept resources and direct map resources. Direct map resources will go directly to SDI on the hardware. So there is no change for that. But for intercept resources, there's a lot more software now in the PF driver to actually compose an SDI, emulate the configuration space if you want to expose the PCIe device to the VM or container. If you want to emulate some of the control registers, there's a more logic in there as a part of the virtual device composition. So that's the main change in the software for the PF driver. Also, to provide more composability and flexibility, we also are now providing a way to store interrupts in a device-specific way So there'll be additional code in the device driver to configure interrupts, whether you want to configure as a part of the PF MSI or separate table. So we expect those things in the PF driver around creating SDI, assigning resources to SDI, composing them. We're also going to add additional interfaces from the OS to the driver to actually support live migration. So you can expect some interfaces to save an SDI state or restore an SDI state, reset an SDI, right? So all the hooks which were initially in the config space now are being given into the PF driver to manage that control path. And most of this work has been done already by the frameworks of the OS, as Jake mentioned earlier, right, for security reasons or for other reasons from hyper's perspective. So we're going to leverage that and add additional interfaces for SIOV.
Okay, so Karsh, I'm gonna stick with you here. So for SIOV technology shifts more control and trust to the host software, while PCIe TDIS technology explicitly removes the host from the trusted computing base. How do these two approaches interoperate in practice?
Yeah, very, very good question, Scott. So as you mentioned, right, like the whole idea behind the TDIS was to remove the host or the VMM from a trust boundary, whereas with the SIOV, we are giving more power to the host, right? So there are a few implications of it, right? So one implication would be that in TDIS, we already have a state machine where there's a config unlock state, config lock state, and the run state and error state. So here the idea would be that device could still keep the VMM in the TCB to configure the device, but then we can reuse the TDIS report for device to report out the configuration to the VM, like TVM, to verify before it brings as a part of TCB. So here device would need a chain to actually report out the configuration as a part of the lock state to TVM and let the TVM device driver software verify that state before trusting the device with its secrets. So that will be a specific thing you would need to do as a device vendor. Apart from that, the other implication would be that with the SRIOV, the bars were different between the VF and the PF. With Scalable IOV, you are kind of sharing the PF bar for your TDIs, right, as well, right, with our SDIs for Scalable IOV. So now we also would need some way to know which MMIO regions, right, or pages are assigned to physical function versus SDI. So you can do correct access control on those MMIO regions. So you would need a way to associate within the PF bar which regions map to which TDI.
Everything Utkarsh said is true. I want to talk about the software here for a moment. So if you're thinking about confidential computing in TDIS, and I spend a ton of time on this, and then you look at Scalable IOV and you ask yourself, what have we done here, right? What we've said is that a lot of the traditional functionality of the control plane of the device, not the data plane, right? We want to leave the data plane pretty much as it is, but the control plane of the device gets pushed somewhat out of the device and more into virtualization layer software. If the implication of that is that we now must trust that virtualization software as part of the TDIS scenario, we will have failed, right? No one believes that we want to pull an entire copy of Linux or an entire copy of Windows or any other hosting system into the trusted computing base of the customer's confidential machine, confidential VM or trust TEE VM. So I believe that we absolutely must build these systems so that that part of the control plane is outside of the trusted computing base or TCB. And in order to do that, the implication is that we need to do the same kinds of things in the device interface report that we do with PCI with the control plane of the device interface. So for instance, we have recently started this standardization in the NVMe group to try and talk about what it means to lock a device with TDIS in such a way that that we do not have to trust most of the control plane of the device. And for NVMe as an example, that's things like measuring the state of the definition of the admin queue, because you have to be able to trust the admin queue. And moving all of that, I mean, I'm really glossing over a lot of details, and there's not a good way to go deep here now. So that isn't going to make a ton of sense by itself. But I think what the general implication of Scalable IOV is that you want to let the control plane run, set the device up, lock it, measure it, decide if you like the measurements, and when you put it in the run state, then the control plane can't change at that point. And what that does is it allows a lot of the device firmware and all of the virtualization software we're talking about for Scalable IOV to be outside of that trusted computing base.
Okay, thanks, Jake. Rob, you've been patiently there. So from a device vendor's perspective, what are the key design considerations and benefits of adding SIOV technology support to an endpoint device?
Yeah, so obviously SRIV's been around for a long time in endpoints, but whilst it's been there for a long time, it doesn't come for free. So SRIOV or any current virtualization technique from PCIe requires a certain amount of ASIC area and memories to handle the separate MSIX tables, bar configurations, and even just for a small number of virtual functions. So in the small hundreds, that's adding a small few millions of gates to an ASIC. That all takes power consumption and adds design complexity. So to Jake's point earlier, where he was talking about the difference between or the need for SRIOV versus SIOV and scalability, from an endpoint vendor point of view, scaling SRIOV becomes very, very difficult, just from a pure cost and complexity point of view. In addition to the actual physical cost, there's then a validation cost. So for every different type of scenario that you could possibly run the endpoint through, so a mix of PFs and VFs, you have to go and actually validate every single one of those different use cases. So SIOV should simplify that validation significantly. Because it abstracts everything back to the software layer, you should be able to verify a small number of SDIs rather than all different types of possibilities that you could come up with PFs and VFs. So there's quite a large validation cost to that, and it takes a long time to do it.
No, absolutely.
So from an overall scalability point of view, then that as an endpoint, SRIV has a very fixed limitation, at least from my point of view, or a fixed number of VFs that we really don't want to go beyond. Otherwise, endpoints start to become very, very complex and costly. And there's still a lot to learn yet on SIOV as well. So, but at least from a hardware point of view, it's not looking as impactful as SRIV.
Okay, thank you. So, Steve, how does Scalable IOV leverage existing root complex hardware and translation agents?
It does. It leverages them a lot. I mean, there was a question on the chat about how certain parts of the PCIe topology have to change for SIOV, and the answer to some of that is it doesn't, right? So things like retimers, even PCIe switches to some extent, they're somewhat below the layer of SIOV, right? SIOV is essentially a feature of PCIe, and it is carried above the physical layer, and so things like retimers certainly won't be affected. But one thing that plays a pretty big part here is the translation agent, IOMMU, whatever you want to call it. And the example I gave earlier about a move towards accelerator-initiated I/O, that's a space where we're very much looking to SIOV and the translation agent to help provide security and isolation. So, just to give you an example, if we get to a place where we want to assign NVMe controller doorbells and queues to a GPU so it can initiate storage I/O, right? And that's something, multiple accelerator companies have been talking about doing. Then ideally we would like to have a way of setting up an IOVA, so basically an IO virtual to physical address mapping in something like an IOMMU. And the only way that we can do that right now is if we have some way of differentiating traffic based on what queue was utilized. Now with SIOV, we can actually take queues from a PF and assign them in hypervisor software to a specific SDI. And then we get basically a routing tag for that particular queue. So in theory now, I don't need SRIOV. I can use SIOV, SDIs, some clever software in the hypervisor, and I can take a single NVMe controller and create a whole bunch of NVMe SDIs that each have one queue, right? As opposed to one controller having 128 or whatever queues. And that queue, because it's associated with one SDI, gets a specific router ID tag. I can create a IOVA mapping for that router ID tag, and I can basically ensure that even if my GPU code is either incorrect or maliciously altered, I'm not going to suddenly initiate a DMA from an NVMe drive to a set of addresses that I really do not want that particular NVMe drive to overwrite with data from NAND, right? It's a great way of enabling this ability to hand out just small amounts of resources, a single doorbell or a couple of doorbells, a single IO queue, a couple of IO queues. And this works for RDMA, it works for NVMe, it works for data moving standards like SDXI, it works for vendor specific programming interfaces, and it gives us that isolation. But it does require the translation agents and the IOMMUs, and it will require, to Jake's point, a lot of software at the middleware layer. So in the Linux kernel, in the hypervisors, that's an area where there's going to have to be a bunch of work done. But I think we'll be able to do some very exciting things in terms of I can make my SDI look like anything. I can make it look like an NVMe drive that has some special features. I can make it look like a mix of a couple of different things. I can even create my own unique SDI and have my own unique Linux kernel driver for it and have that running inside my VM. So there's a whole bunch of fun and games that I can play there. But in order to get that isolation, that's really where I need that translation agent support and that routing ID that's unique to each SDI.
Thank you. So Yukarsh, kind of following on, there was a couple mentions here, but so what are the key advantages of Scalable IOV's MMIO virtualization via page tables?
So the main benefit, like as Steve mentioned, right, that you want to assign different queues to different VMs. So now you can just rely on the page table mapping, right? So you can say I have a big PF bar with 100 queues. So I can just now say assign each of those queues to individual SDIs, and then can rely on the page tables, like a second stage page tables, to map those virtual machine directly to the SDI. And if you want to add more queues, right, you can just add one more mapping in the second set page tables and add one more queue to SDI to dynamically increase the number of queues for SDI or reduce it based upon demand. So it provides you more flexibility where you can add more resources, reduce them. Also, it doesn't have to be sequential, right? So given you can use page tables to provide the queues which are non-sequential in the PF bar. So you can also create a SDI with a first queue in the PF bar, second queue, and then 10th queue, and then 20th queue. So you can, it doesn't have to be sequentially mapped in the PF bar. It could be scattered around, and you can still map them as a continuous 4 queues to a VM using page tables.
Okay, so we have a few minutes remaining here. And let's try this one. So Rob, what's the motivation for supporting SDI strided RID mapping for SIOV?
Well, I wrote that part of the spec. Go ahead, Rob.
So hopefully it's I was going to say hopefully it's an easy one, because backwards compatibility was the reason. Obviously, SRIOV supports the strided RID mapping today. SIOV also supports that, so as well as supporting from a host perspective. So if you were wanting to move to SIOV and you wanted to keep with the same, or I guess Jake would be able to tell me exactly how it works, but from to keep the same software structure, you should be able to then map to SIOV in a similar way. So
I don't think it actually just preserves the software. What it preserves is the hardware, right? If you have an existing hardware design and all you want to do is relax the rules of SRIOV so that you don't have to do as much of it, you will end up with a hardware design that has a strided RID mapping. And so you would have to make your existing hardware IP changes more complicated if you wanted to move away from a strided RID mapping. So we left that as an option in the spec. But what it doesn't allow is to use, for instance, all of the available requester IDs underneath a root complex in as efficient a way. And so, for instance, if you have a future system with multiple segments going to the same endpoint, which is certainly under discussion in the PCI SIG, and people are trying to enable that, you would have a larger requester ID space, and it would be non-contiguous. And then the strided RID mapping doesn't work for you at all. So we left the strided RID mapping in as an option so that existing designs work, and we left a more flexible option in there for a future where you would want to use RIDs in a non-contiguous way.
Thanks, Rob.
Thank you, Jake. That was a better answer than.
And Jake. Okay, one last question here. So, Yukarsh, looking ahead, how does SIOV technology lay the foundation for fabric attached, composable, and hyperscale systems?
So as like Jake mentioned, right, we are seeing a demand where there could be a one device with multiple links, where one link could be going to one root port with a one corresponding IOMU or TA, and then second link going to second IOMU or TA. Other example would be like what even Steve mentioned, where there's one device where I want to send one of the traffic to one side and other to other side. There also could be a rack system where I have multiple hosts, where I want to use one set of SDI with the one host and second set of SDI with second host. So for all those cases, you need a way to dynamically assign the routing ID or request ID to SDI. So with SIOV, we provide that, where you can, based upon how the root ports are mapped to the IOMU or TA, you can kind of program corresponding routing ID to the SDI. So that's the ability to assign dynamically routing IDs and also non-sequential routing IDs. They're also going to be one key factor to provide more composable, more scalable, multi-link, and multi-host platform in future.
Okay, thank you, Yukarsh. So as we conclude here, I want to thank everybody for joining. Rob and And Yukarsh, Steve, Jake, and Steve, appreciate you spending time here with our audience. Any last minute closing statements, even though we're here at the top of the hour? If not, we want to thank everybody for joining us for this last hour and hope you found it educational. And thank you, everybody, for joining.
Thanks,
Yeah,
everyone.
thanks for a great panel. Thanks for attending.
Thank you.